Good afternoon, Martin. At the moment, there's only yourself, but we're hoping to have more people join in the next few minutes. But we're going to make a start because we only have a short period of time for these sessions. So we're very lucky today to have David Peterson from IBM to talk about, yes, it's possible. You can achieve true continuous availability for your critical applications. So this is going to be a very interesting session. And just one thing, uh, as there's only a small number of attendees, I'm going to allow you to unmute your mic. So David is happy for you to ask questions throughout the session. So with that, I'm going to hand over to David. Thank you again, David. And it's all
Okay.
yours.
Okay, thank you. Hello, Martin. Um, Please feel free to ask any questions since you're the only one here, so we can answer any questions you may have. So my name's Dave Peterson. I'm responsible for the GDPS solution. GDPS solution will provide availability, disaster recovery, and cyber protection for basically mainframe clients. What I'm going to do today is take you through one of the most recent GDPS products called GDPS Continuous Availability. So you've all seen charts like this that says, you have to worry about your availability. And as a society, we have become more and more dependent upon IT. And when the IT is down, um, the impact on your customers, your brand, etc., becomes a big factor. There's all sorts of data available on the internet that talks about the impact of outages. But there was one interesting study done a while ago, that basically noted that as businesses digitally transform, IT outages are unacceptable. But the statistic is very interesting. 40% of the businesses never reopen after a disaster. And of those that do, 25% fail within a year. There's all sorts of data here that talks about the average cost per outage. You can have banking and finance, it can be up around $9 million. Across all industry sectors, it's approaching $7 million. And this data is like a couple years old, so it's gone up. The impact of outages, though, clearly is lost revenue, lost productivity, lost reputation. Additionally, within the US, the European Union, the regulations have gotten more stringent. In the US, there's the FFIEC regulations that come from the OCC, the Fed, the Treasury, and the European Union. There's DORA, etc. But more and more of these are basically making sure that the IT is more resilient. So let's jump into it. What is GDPS continuous availability? Under the GDPS solution today, we have a great portfolio of products that can provide availability, disaster recovery, and cyber resiliency. But we call those the classic products, and those are based upon DSAK copy services, disk-based replication, such as MetroMirror, Global Mirror. This is different. This basically can provide great RPO and great RTO. So for instance, if you were to have an unplanned outage for a specific workload, such as retail banking, you can have an RTO of 30 seconds. This also, for planned outages of a given workload, you can achieve a similar RTO of seconds, not minutes. So this thing that we call GDPS continuous availability is revolutionary in that it can dramatically improve the RTO, and it works at a workload level. So let's contrast this GDPS continuous availability against one of the existing GDPS solutions. So first we have GDPS Metro. GDPS Metro is a multi-site sysplex, and the sites could be logical or physical. Logical means they could be in the same data center. They could be halls in a data center, pods, or it could be actually two different physical data centers. But if you are running a GDPS Metro and it's spread across 2 sites, again, either logical or physical, and the applications are Sysplex enabled, and the critical data is being mirrored, you can run what we call a multi-site workload configuration, where if one site fails or one site has to be taken down for a planned maintenance activity, the other site can absorb the workload. But the limit here is that you're using synchronous replication to replicate the coupling facility structures, updates, to replicate the updates to disk. You're using synchronous protocols. And as you increase the distance between the 2 sites, site 1 and site 2, signal latency becomes a bigger and bigger factor. A good rule of thumb is that every 100 fiber kilometers, fiber, it refers to the distance that dark fiber goes to the ground. But for every 100 fiber kilometers that signals have to go through, you're introducing about 1 millisecond delay. So we can achieve near continuous availability with GDPS Metro with a multi-site workload, but you're limited by distance. GDPS continuous availability can provide the comparable function, but at unlimited distances. We have another product called GDPS Global, but this is a disaster recovery only solution. It works on a Sysplex basis, not at a workload basis. And when you go to do a failover or a planned switch from the production region to the disaster recovery region, you have to move everything. And that could take an RTO or recovery time objective of an hour or so based upon client feedback. Continuous availability works at a workload level, and we can do a switch in 30 seconds or less. So GDPS CA is targeted for those applications that need the best availability possible, RPO and RTO. And this can complement your existing GDPS solutions, either GDPS Metro or GDPS Global, or 3-site, 4-site. So this is what it looks like. We have 2 Sysplexes. We have Sysplex A, that's in region 1. We have Sysplex B, that's in region 2. Each Sysplex has the same data, the same applications. Out front, we have intelligent load balancers, such as an F5 running in LTM mode. We keep the 2 Sysplexes synchronized by using software replication. We support DB2, vSAN, and IMS. Oops. But what happens here is that we'll set up the F5 to basically route all IP connections coming in, let's say, to Sysplex A. Sysplex A will process transactions asynchronously as those transactions perform commits. They'll be replicated asynchronously from Sysplex A to Sysplex B. If and when there is a workload outage or a site plan maintenance activities, all we have to do is redirect the IP connections from Sysplex A to Sysplex B. There's no need to do a restart of the Sysplex because everything's up and ready to go on Sysplex B. All we're doing is redirecting IP connections. Additionally, we can do the same sort of thing with MQ connections coming in. Outbound from this Sysplex, you can have MQ or distributed queue managers, and we can just redirect the channels to MQ channels. By doing this, not requiring a restart of anything, just redirecting channels, redirecting IP connections, we're able to achieve an RTO recovery time objective of 30 seconds or less. And based upon the configuration, if you're using it, we can achieve an RPO typically of a couple seconds. So the benefits of this GDPS continuous availability are for unplanned outages, where an unplanned outage could be either a application has failed, a workload has failed, we detect this by monitoring the middleware that makes up a workload. Or a site has failed. We're monitoring the LPARs in the site. So when we detect a failure, either a workload or a site failure, we can switch away from the failing Sysplex, the failing workload, to the alternate. By doing this and routing away from sick but not dead cases, we can improve performance, and recovery time is reduced down to about 30 seconds or less. For planned workload switches, we can again reroute workloads from one site to another site very quickly, 30 seconds or so. This gives you greater availability. And then if you were in a sick but not dead case where a site or a Sysplex was not meeting its SLA, you could do a workload switch. But both for planned and unplanned workload switches, we're able to do 30 seconds or less RTO, whereas using traditional disk replication, we're talking probably about an hour or so. So let's go into it in a little more detail. So this provides the ability for, again, for planned and unplanned outages at a workload level or a site to distribute the workload across multiple sites and route around failed sites. When it comes to unplanned outages, we can detect workload failures by monitoring the middleware that makes up the workload. We can detect site failures by monitoring the LPARs where the workload runs. And then if we detect either an unplanned site failure or workload failure, there's two modes to perform the switch. One of those is automatic, where we'll do it automatically as soon as we detect the outage, or we'll put out a prompt operator, W2R, and wait for the admin to respond to it. But we're able to do the switch very quickly. So let's go through what a graceful switch would look like for a planned scenario. The first step we'll do is basically when we go to do a planned workload switch from Sysplex A in region 1 to move a workload over to Sysplex B in region 2, we'll basically quiesce all the workload that's running for the given workload. We'll quiesce it. We'll stop batch. We'll let existing transactions drain. We'll make sure that all the replication updates for transactions that had just completed on Sysplex A have been replicated over to Sysplex B. We have this concept called fence. And what that does is it puts the data objects, such as the DB2 tables, into a read-only mode if we're in the standby site, and an update mode when we are in the production site or the active site. So we'll drop the fence and the site we're going to, that would be the workload running on Sysplex B. We'll put the fence up on the workload running in Sysplex A, and then have the F5 redirect connections over to Sysplex B. And Sysplex B now becomes the active workload instance. You go home again, the graceful switch failback is similar. We'll have to, if we moved the active workload instance from Sysplex A to Sysplex B, we'll have to resync the updates that are on Sysplex B. Once they're back in a duplex state, then we could do a graceful switch to move back to make Sysplex the active workload instance be on Sysplex A. Additionally, the solution consists of all sorts of monitoring to make sure that everything is ready when you want to go to do a switch. If we find that something's not ready, we'll generate alerts so you can fix things before you need this capability. And again, we use soft replication to keep the two Sysplexes in sync. The soft replication is done at a unit of work level and will support DB2, IMS, and vSAN. But this maintains the ACID properties, and the replication is done asynchronously. The way this works is in sysplex A if that was the active instance of a workload. After transactions commit, there's a function called the capture engine that queries the active DB2 logs for looking for committed units of work. When it sees a committed unit of work, it will put that into an MQ packet, send it over to the other sysplex, in our case here, sysplex B, and replay that transaction. Typically, the latency is a second or two to do this. The product behind all this is known as IBM InfoSphere Data Replication Server 4. And again, we support DB2, IMS, and vSAN. So we support different configurations with this solution. The first one is what we call active standby. And this is the same picture that I showed you before. What we have here, though, is a little animation that will help explain things. So we have sysplex A that have the active instance of a workload. On sysplex B, we have the standby instance of the workloads. Inside sysplex A and sysplex B, you'll notice some boxes, but that's the middleware that makes up the application, such as Kix DB2. So sysplex A has one or more workloads. Each one's in this active standby configuration. Sysplex B has the same workload, sitting there idle. They also have the same data. So basically, sysplex A and sysplex B are clones of one another. Sysplex B is sitting there ready to take over when needed. They keep the two sites synchronized. We do use soft replication. Again, that's the IIDR for IMS, DB2, or vSAN. It's done asynchronously. It's done at a unit of work level so that we can have unlimited distance between sites. Out front of the sysplexes, we have these intelligent load balancers, such as the F5, running in LTM mode, local traffic mode. But this allows us through software to pass commands to the F5 to say where to direct IP connections. So we direct all the IP connections to sysplex A. So sysplex A is the active instance of the workload, and sysplex B is the standby instance. When transactions flow over those connections, they come into sysplex A, they get processed. When they're committed, soft replication will take those committed units of work and replicate those asynchronously over to sysplex B. Now we're monitoring things continuously. If there is an outage to the workload or to the sysplex, we'll detect it pretty quickly. And then there's two modes that when we go to do a switch for an unplanned outage. One is automatic. So automatic just says when we detect an outage, switch automatically. Or there's the manual mode where we put out a prompt and wait for the admin to respond to it. But assume it's automatic mode. Within 30 seconds after a failure detection interval, we'll detect the problem and just inform the F5 to redirect all the IP connections from sysplex A to sysplex B. If it's manual mode, the prompt will be issued to the admin, and we will wait for the admin to respond to the prompt. Once the admin responds to the prompt, we will basically tell the F5, redirect all IP connections over to sysplex B. And clients that are using this typically are achieving about a 30-second RTO. To go home again, sysplex B is tracking the updates that were made while the active instance is running in sysplex B. So to go home again, you'll basically issue a command that says replicate those updates from sysplex B to sysplex A. Sysplex B is effectively doing change recording. So once sysplex B and sysplex A are back in duplex state, you could then basically go back again. make Sysplex A, if you wanted to, become the active workload instance again. The time to do this resync is proportional to the time that you are running over on Sysplex B. We also support MQ channels coming into the Sysplex. To do this, we use a facility in MQ called MQ clusters. Outside of the Sysplex, we have distributed queue managers. And we have queue managers also running on Sysplex A and Sysplex B. But we have things set up to have the distributed queue managers send all the MQ messages to Sysplex A. So when transactions come in over these channels, they get executed on Sysplex A. When they commit asynchronously, those updates are replicated over to Sysplex B. When there's a failure, we'll detect it and basically interact with MQ to redirect all the messages now to be sent from the distributed queue managers to Sysplex B. And we'll go through the same sort of scenario when Sysplex A is repaired and brought back up again. Sysplex B will resync back to Sysplex A. Now, in the presentation here, we talked about like it's two different things where we have IP connections and we have MQ channels. The processing allows us to support IP connections, MQ channels, or both. And most clients will be having both. We just don't have a way to depict that easily in graphics here. So that's the active standby configuration. The active standby configuration supports both MQ channels coming in and IP connections. And we can do a planned workload switch, an unplanned workload switch, typically in 30 seconds or less. Similarly, we can do things at a site level where we would move each workload for a planned site switch or a unplanned site switch. We would move each workload in parallel. The next configuration we support is what we call an active query workload. The idea here is that we have an active standby workload running between Sysplex A and Sysplex B. But we also can take query transactions, read-only transactions, and spread those across Sysplex A and Sysplex B. What we're going to try to do is route most of the query transactions to Sysplex B, because that's where the standby copy of data is. So what we're going to try to do is have most of the update transactions go to Sysplex A. Most of the query transactions go to Sysplex B. We have metrics and instrumentation that track how current the data is on Sysplex B. If the data on Sysplex B becomes too old, then we'll redirect those query transactions to Sysplex A, where the update copy of data is. Similar here in our scenario, if Sysplex A fails or the workload, the active standby workload fails, what we'll do is do a failover to Sysplex B. The active standby workload will result in the active workload instance being on Sysplex B, and we'll redirect all query transactions now over to Sysplex B. Again, typically here we can achieve this in about 30 seconds or less. And the go home scenario is the same as I showed previously. Sysplex B has updates on it. After repair action's been done on Sysplex A, or Sysplex A is brought back up after maintenance action, we'll resync the updates that were made to Sysplex B back to Sysplex A. Update transactions can be routed to Sysplex B, and query transactions will be routed over to Sysplex A as much as possible, because that's where the standby copy data is. So let's go into a customer example. So this is a large Chinese bank. And they have 6 workloads, 6 active standby workloads and 1 active query workload. The largest of the 6 active standby workloads is for domestic banking in China. They have 300 million customers, 500 million accounts. So it's a huge DB2 database. They also have another workload for commercial clients in China. And then they've got 6 other workloads that handle their operation outside of China. One for Latin America, one for North America, one for European clients, and one for AP, Asia Pacific. We can do a planned workload switch of all these workloads in less than 30 seconds. If there was an unplanned outage, similarly, we'll detect it and we can switch all 6 in less than 30 seconds. The benefit that they have achieved, though, is largely when they do application upgrades or middleware upgrades, they can do upgrade, for instance, Sysplex A first, then go to Sysplex B. So for example, when they recently upgraded DB2 from one version to another version, they did a workload switch from Sysplex A to Sysplex B. So they did a graceful switch over to Sysplex B. That took them less than 30 seconds. At that point, they were able to upgrade the DB2 on Sysplex A, and they set it up to be running in compatibility mode. Once they had completed that, they did a workload switch back from Sysplex B to Sysplex A. And they did a similar upgrade to the standby copy data running in, or the DB2 for the standby workload instance on Sysplex B. They ran this way in compatibility mode for a month or so just to make sure that things were running all right. And then once they were confident that the new version of DB2 was all right, what they did then is just switch to the new version of DB2. Previously, when they would do a DB2 upgrade, it would require a 4-hour outage during a change window. Now they have a brief service interruption to do these 2 30-second workload switches. So it's dramatically improved their availability to do maintenance upgrades of software, system software, middleware software. They also do major application upgrades monthly. So this allowed them to do workload upgrades with minimal interruptions. Again, it would take them 4 hours. Now they can do it in 30 seconds or so. Additionally, because they are also using an active query workload for their consumer banking workload, they're able to distribute query transactions, such as what is my balance between the 2 Sysplexes. So they're very happy with it, and we dramatically improved their availability because they're able to keep things up when they would have incurred planned or unplanned workload or site switches or outages. So that's about all I have in the presentation. There is some further documentation, and in the backup, there's some more detail about the specific products. But that's basically all I had. So Martin, are there any questions that I could answer or you could ask that I could answer for you?
You should be able to unmute, Martin. Let me just check. Yeah.
No, nothing from me.
Okay, well, thank you for joining. And if you would like more information, please let us know.
Yeah, thank you very much for that. It's really interesting. And like I was saying earlier, as it's all going to be recorded, there'll be lots of people watching it over the next few weeks, and maybe you'll get some more questions then. Please, Martin, if you can do some feedback for us, as it's always important for us to plan, and it's important for David as well, to see what we're doing right and what we're doing wrong. So we've got another session in this work stream 8Q, world-class high availability and disaster recovery, with IBM GDPS next. Is that with you, David? I don't know.
No, that's someone else on my team, Tanya
Ah.
Buchanan.
Okay. So yeah, so enjoy the last few sessions of the conference.
Okay, thank
Thank
you.
you very much.
Cheers. Thank you both.
Bye.
Bye.